Okay. Just a note before going on. I talked about stationarity, and I also mentioned, before talking about non-stationarity, I also mentioned that hydrological processes are affected by seasonality. Seasonality means non-stationarity, by the way. So this is just a note, a remark that I wanted to make before going on. Okay. Stochastic processes. We involve stochastic processes and theory of stochastic processes because we want to be able to generate synthetic data by preserving both the autocorrelation structure and the memory of the system. And I wanted to say both the probability density of the data and the memory of the system. And we know how to model the probability density of data by using suitable probability distributions. Now we have to learn how to model the memory, how to reproduce the memory of the system. Memory means that the system remembers its past, and means that the past has an effect on the future. And if this is true, it means that there is a structure in the observation. There is a kind of relationship between subsequent observations. And therefore we have to make an assumption about this relationship. We have to make an assumption about how a river flow observed today remembers the river flow observed yesterday and the day before yesterday. So we have to make an assumption about, as I said, a relationship between subsequent values. And the simplest thing is to introduce, as I already mentioned, a linear assumption. The simplest thing is to assume that the dependency between subsequent observations is linear. Linearity is always an attractive solution because linear systems are easy to deal with, as we will see. What means to assume linearity? It means that we assume that the river flow can be represented, can be written as a linear combination of past values. So let me indicate with x, with the index t, the generic variable, hydrological variable observed at time t, and this can indicate river flows or rainfall, whatever, temperature, whatever. We work in a very general framework here. And let's then express x observed at time t as a linear combination of past values. So we can write x observed at time t is equal to a coefficient, let's call it phi1, which multiplies x observed at time t minus 1 plus phi2, which multiplies x observed at time t minus 2 plus plus phi n x observed at time t minus n. To this relationship, we have to add an error term, because if I just leave this relationship as it is written there, this would be a deterministic relationship, which of course wouldn't be correct, because indeed this kind of relationship is affected by uncertainty, it's not deterministic. So you have to add a deviation, an error term. Let's indicate it with the symbol epsilon at time t. what is the purpose of this linear relationship? The purpose is to explain the memory structure again. We observe that there is memory in the data, and we introduce this linear function to explain it. Here we have some parameters, the phi's, that are included in this relationship, and also we have this error term here. And now we should better understand what are the conditions for this relationship to work correctly, and also we have to understand what's the meaning of these parameters and this error term. This process, this is a stochastic process. And why it's a stochastic process? Because, of course, you see that here there is a modeling of a family of random variables, which is the x observed at different times. And this is not a deterministic model, it's a stochastic, because here I have a deviation, an error term, from a deterministic relationship. And it's stochastic because, as we will see, this deviation is random. We assume that it's random, and therefore the process is stochastic. This is precisely called autoregressive process or autoregressive model. And it's also identified with the acronym AR. Let me make a correction here. Sorry, let me use P instead of lowercase m. Okay, because it's more appropriate. The terminology used by textbooks very often use the symbol P, and this is called the process ARP. It's called the autoregressive process of order P. Now, this process, this relationship, in general, it's not correct. And not only it's not correct because we have to introduce an error term, but it's also not correct because in many cases it does not provide a convenient representation of the memory structure. So we have to identify what are the conditions for this process to work well, because this allows also to understand what are the checks, the tests that we have to make to verify that the process is acceptable. Okay, so let's now clarify the assumptions, but before going on, let me refer to a simplified form of this process. Let me refer to the AR1, which is a widely used process, and it's easier to write with respect to the autoregressive of order P, and we can write it just x in this form. Xt is equal to phi 1 x t minus 1 plus epsilon t. This is the AR1 process. Easier to write, as I said. And let me now clarify what are the assumptions. Assumptions that must be respected in order to provide a satisfactory representation of the reality, which does not mean that the error is eliminated. The error is never eliminated. But even if we introduce an error term, the representation must be satisfactory. What I mean with satisfactory is that I'm not expecting that the process precisely reproduces the variable because there is the error term, so I'm not expecting that. I am expecting that the process reproduces well the memory structure, the autocorrelation function. This is what I am expecting. So let's identify what are the conditions, the necessary conditions to meet in order to achieve this goal. Okay, so we have 4 assumptions. First of all, the first assumption is that Ex must be equal to 0. If the average is not 0, if the mean value is not 0, this is not a problem. You can just reduce the time series to the 0 value by subtracting to each observation the mean value. If the mean value is different from 0, you just subtract from each observation the mean value and you get this condition. So this is not really a big problem. But if you want to write this model in this form, the average must be 0. Second, the process must be stationary and Gaussian. Meaning that you cannot represent with an autoregressive formulation non-stationarity. And you can easily understand that this is true because if you get a series with the mean value that is equal to 0, you cannot, with this autoregressive process, to change the mean value in a convenient way. So it must be stationary. So if you have climate change, this process cannot describe it. You have to make some modification. And also if you have seasonality, this process cannot describe it. So we will have to solve this problem. It is not able to reproduce averages that vary during the year. Okay, Gaussian. Why Gaussian? Why the X should be Gaussian? It's quite easy to understand this. Why this condition must be met. Here you see that you have two random variables that are expressed, that are related by a linear combination. So you have the random variable xt, which is related through a linear relationship to the random variable observed at time xt minus 1. But these two random variables at the end are two occurrences of the same random variable. Because as you advance with time, you get xt plus 1, which is equal to phi 1 xt plus epsilon t. So you see that the first random variable here, then as time passes, goes to take the place of the second random variable here. They exchange continuously. So basically, you cannot change the probability distribution of these variables. Because if you get here an xt, for instance, that is normal, and let's suppose that xt minus 1 is not normal, let's say that it's exponentially distributed, then you get here normal, but when you go here with the same random variable and you put it in place of the other one, of course, you cannot get a log normal variable by a normal one, but by just changing the place. So you understand that both xt and xt minus 1 must have the same probability distribution because you change them continuously. You put one in the place of the other, so you have to get the same probability distribution. But on the other hand, you note that the xt is obtained as a linear combination of xt minus 1. So if you have a Gaussian distribution for xt minus 1, and you transform it linearly, you must be sure that this linear transformation ends up again with the Gaussian distribution. So basically, what you have to make sure of is that the probability distribution is preserved through this linear transformation. And there is only one probability distribution that is preserved through a linear transformation, it's the Gaussian. The other distributions are not preserved through a linear transformation. If you take a log normal and a linear transformation of the log normal, you don't get a normal anymore, because you get, as you go on, a Gaussian. Because I said at the beginning that if you average, so you take a linear combination of any random variable, you converge to the Gaussian distribution. And therefore, this means that any linear transformation of whatever probability distribution converges to the Gaussian distribution. So it's not preserved, the probability distribution, through a linear transformation, unless it is Gaussian. So you understand that in this case, we want to use a linear transformation, but preserving the probability distribution, and therefore we have to introduce the assumption that the data are Gaussian. And this is another complication, because we know that hydrological data are often non-Gaussian, and this means that, again, we have to solve a problem here. Okay, then, two more assumptions with a very well-defined physical meaning. What is the purpose of this linear structure? To represent the memory structure. It means that you have a random variable, a process, that has a memory structure, and you want to reproduce it. If you want to reproduce it, it means that this linear relationship should be able to give a good interpretation of this memory structure. Otherwise, if the linear combination is not good, of course you don't reproduce the memory structure. How to check that the memory structure is well reproduced? Well, there is one simple way for checking this, and it consists of looking at the deviation, looking at the error term. This error term represents the deficiency of the linear structure. This deficiency is therefore sure, because we expect that the linear structure does not provide a deterministic representation. So the error exists for sure. But at least we expect that the linear structure explains well the memory of the system. And if the memory of the system is well explained, it means that the error term shouldn't have any memory left. Okay, this concept is important. If the linear structure is able to represent at least the memory of the process, it means that the deviation term shouldn't have any memory left. And therefore, to translate in statistical terms, epsilon must be independent. What does it mean independent? It means that the autocorrelation function should be identically zero, except for the first coefficient, which is 1. Autocorrelation function identically zero, identically null. Okay, then let's write it here. Rho L equal to 0 for any L different from 0. There is one more check that we should do. Which is, in a way, it could be assumption 3 and 4 could be joined under the assertion, the statement that epsilon is independent. But usually I prefer to keep them separated, which means that epsilon must be independent of previous outcomes of x. Epsilon must be independent of previous outcomes of x, which means that even if you knew past x, you can't predict future epsilon values. And the way to check it is cross-correlation. Cross ACF. Cross ACF is not correct. Cross correlation. I wanted to use the acronym because it's difficult for me to write here, but cross correlation. You must check that the cross correlation coefficient is 0 for proper values of L. Proper means that they must reflect the fact that epsilon is independent of previous x. Epsilon is not independent of concurrent observed at the same time x. There is a dependency. You see, this relationship establishes a dependency between x at time t and epsilon at time t. So I can admit a cross correlation at lag 0. What I must be sure of is that there is no cross correlation between epsilon and previous x. These are our assumptions. So basically, once that you apply this process, and we will see in a few minutes how to apply it on a series of data, how to estimate the parameters, you have to check that the data are Gaussian, and Gaussianity applies to both x and epsilon. They have to be both Gaussian. You have to check that epsilon is independent, and you have to check that the mean is 0, and you have to check that there is no cross correlation between epsilon and previous x. And to check stationarity is a bit more difficult. We will see, because stationarity, strictly speaking, is impossible to check. And we will see how indirectly we can make some checks that tell us whether no stationarity is present. But there are no statistical tests, no formal statistical tests for stationarity. So now the question is, okay, I know the process, I know the assumption, how to apply the process. So let's suppose that I have a river flow series, and let's suppose that I want to apply a AR1 process. What should I do? Applying, fitting, let's say, a process to a time series means to estimate phi1. In the case of the AR1 process, we have to estimate this parameter. And we also have to be able to check the assumptions, in particular on epsilon. So first of all, before you start, you should check that the series is Gaussian. If not, you may, for instance, take the logarithm of the series and then apply the stochastic process on the logarithm. You should check that the data are 0 mean before starting, and if not, you have to subtract the mean from the observations, and then you can apply the model. Let's see, it's very simple to apply this process, because let's suppose that you have some observed data. And let's suppose that you work with an electronic sheet like Excel. First of all, let's put the data in one column. Of course, it can be done also in R. I'm making reference to Excel because it gives a visual reference. Let's put the data in a column. We have the X. Let's put the data here. And let's now suppose that what we have to do now, we have to estimate this value of phi1. So let's put in a cell of Excel the value of phi1, a trial value, let's say 0.5. And then let's, for this trial value, to compute here on the right, a column which is given by the relationship xt equal phi1 xt minus 1. You can compute this relationship starting from the second data value, and then you go forward until the last value. You could compute also this relationship for the first one, indeed, because there is a rule that you may use in statistics. When you need the value of a variable which you don't know, like in this case, if you start from the first time instant, you don't know xt minus 1, because it was not observed. But when you don't know the precise value of a variable, the rule is to take its mean value. In this case, the mean value is 0, so you can compute this relationship by adopting at the first time step 0 as value of the previous variable, which means that given that this is a multiplication, you get a result of 0, which is the mean again. Okay, then you can compute here a series of epsilon t by just inverting the stochastic process as the difference between xt minus phi1 xt minus 1. And then you get a series of epsilons. And therefore you can check first of all that the epsilons are Gaussian. And then you can compute the autocorrelation function of the epsilons and check that is identically equal to 0 for lag different from 0. And also you can check cross correlation. So if you get Gaussian data and independent for epsilon, you are done. It means that your process reproduces well the memory structure of the series. And so you got your purpose. Reproducing the probability distribution, which is Gaussian, in this case, by assumption, and reproducing the memory structure. Keep in mind that this epsilon is independent. Now there is one last thing to clarify: how to generate synthetic data. Very simple. In this case, let's refer to an Excel sheet again. Let's refer to an Excel sheet, and let's first of all generate a series for epsilon. It's very easy because epsilon is independent. You know the probability distribution, which is Gaussian, and you know also the mean, the average, which is 0, by the way. And also you know the standard deviation, because you can estimate it. You have a series for epsilon, so you can estimate the standard deviation of the epsilon. And given that epsilon has no memory, you can generate a series of epsilon by just putting together outcomes from the Gaussian distribution with no memory. So it's very easy to do that. So you just generate your series of epsilon. Now, in 5 minutes, I will show on the PC how to do that. Very easy. With the instruction R norm. Then, here you can compute the synthetic variable xt as the product of phi1 times xt minus 1 plus epsilon. In this case, at the first time step, you don't have xt minus 1, and therefore you take the 0 value for it. So at the first time step, you will have here epsilon 1, and then your synthetic data. And you will get Gaussian data, because if epsilon is Gaussian, a linear combination of epsilons gives Gaussian outcomes, and you will get data with the same memory structure than the observed ones. Now I realize that I forgot to tell you one important thing here when I talked about estimation, application of the model, in particular the first step, estimation of the parameters. I forgot to tell you how to find the best value for phi 1, because I said that 0.5 is a trial value, but this trial value could be not correct. So we have to identify the best value for phi 1. I forgot to mention this procedure, so please let me go back just 1 second and to explain. And how to identify the best phi 1? Of course, what we would like to achieve is to minimize as much as possible the magnitude of the error epsilon in order to make the linear relationship as more precise as possible. So let's now compute here a column with epsilon squared in order to avoid that negative and positive epsilons compensate each other. So I can compute a column of epsilon squared, and then in a cell I can compute the sum of the epsilon squared. And this is the objective function that I have to minimize by varying the value of phi 1. So with R, I can apply a minimization algorithm to find the best estimate for phi 1. And then I can compute the errors and check if they are correlated or not. Okay, let me now turn the projector on. And let's try to make some experiment in 10 minutes. I cannot show you an application to a real series because the real series are non-Gaussian and seasonal. And I didn't explain to you so far how to solve these problems. So let me make reference in R to a synthetic series that now I generate. And I generate it with a AR1 process. So let me start from generation by fixing the value of the parameter, and let's see generation first, okay? And generation is quite easy. First of all, I have to decide how many variables I want to simulate, let's say 1000, and I have to decide the standard deviation of epsilon, which is Gaussian by definition, by assumption, but the standard deviation needs to be defined. Because to generate series, I need the value of the parameter phi 1 and also the value of the standard deviation of epsilon. Let's assume that the standard deviation of epsilon is 1. So first of all, let me generate epsilon as R norm 1000. And this means that epsilon is Gaussian. Let's have a look at the probability distribution, but this is clear. This is the probability distribution, Gaussian. And the mean of epsilon is more or less 0. The standard deviation, square root, variance, epsilon is 1. Okay. Now, what I have to do is to apply the relationship of the stochastic process to get, let me call it x, is equal to what? X let me think. Okay, first of all, what I have to do is to fix x1, which is equal to epsilon 1. Note that to define a vector, I needed to define a variable first. So first I defined x by just writing x equal to 0. And then I put the first value of the vector of x equal to epsilon 1. Because of here, you see. Now I can define x, I hope it gets it, from 2 to 1000 as the product of 0.5, let's say, times epsilon from 1 to 999. Okay, it worked out. This is generation, you see, very simple. Indeed, generation, I forgot, I have to add another